are they going?
It's good. A lot on my mind, but I'm gonna resolve it today.
How do I fix
What's on your mind?
it? That was Anthony from home. All right.
1 second. Hey, I'm not sick. I'm just going through some things, and
That's okay, man. That's okay. Hey,
thanks, man.
that's fine. I'm glad you're here. I'm gonna mute you though. Okay, is that? But if you have any questions, type them into the chat.
Yeah, I guess I'm good for a while. Pure accidents, actually, but I think it's great.
All right. Good morning, everybody. How you guys doing? Doing good? All right. Let's see here. Okay, so this is more graphing, so I might as well utilize the power of technology because it truly graphs better than I do and faster than I do. So let's go here to more. Oh, share screen. Here we go. Share the screen. Oh. Desmos. Oh, it's up already. Wonderful. Okay, so we've already talked about what does sine and cosine look like, all right? So just real quickly, I don't even have to touch some chalk, okay? Remember, here's sine of x, here's cosine of x. And really, I want to kind of have this come to the forefront. I want to make this chat look smaller. Yeah.
You can close it.
Yeah, I want to see if they have questions. So, yeah. Let's kind of close this out here. Nope, nope, nope. Whoops. Okay, where did the chat go? Okay, I don't know where that chat went. I'm gonna have to, yeah, because there's 2 students and they're gonna need to ask stuff.
Oh, you're away.
My goodness. I have no idea where the chat went, so. Meeting controls.
Try clicking participants.
Maybe. That's just this. More.
There you go, there's chat.
Where does it say?
Right, the first option.
Oh, first. There we go. Okay. I'm gonna scroll this down here. Let's minimize this, and this will be something I can put over here. Now, if they have questions, they may ask those questions. Okay. Let's put this here. All right. So here's our sine and here's our cosine. Finally. So remember, cosine assumes its highest value at the beginning because cosine of 0 is 1. And then it starts to go down, and at pi over 2 it becomes 0. Sine on the contrary, assumes 0 at 0, and it becomes 1 at pi over 2. You guys know all this stuff, so it's just graphing it, okay? Now, what about their inverse trigonometric functions? What do you guys think 1 over cosine and 1 over sine would look like? So I will touch the chalk now because it's kind of necessary here. Make sure I'm not off screen. So for cosine, notice we get something like this. Okay. But if this is cosine of x and this is x, what if we had 1 over, and actually, let's give it a different color. A 1 over cosine of x. What could go wrong here with 1 over cosine of x? Because clearly cosine does equal 0 at some point, doesn't it? Namely pi over 2. Again here at 3 pi over 2. So it's going to be dividing by 0 at some points, right? So we can't have cosine of 0. We cannot have it equal 0. That means x cannot equal the cosine inverse of 0, which is equal to, as you see, pi over 2. That's when cosine is 0. 3 pi over 2. That's when cosine is 0. Plus 2n pi plus 2n pi. All integer multiples of 2 pi as well. So, what does that make the graph look like? Well, as you will see when we graph it over there, here the cosine is equal to 0. So 1 over cosine, it will be dividing by 0 there. So what we're gonna do is create an asymptote, a vertical asymptote every time it crosses the x-axis, the value of cosine of x. Because that's when the value of cosine of x is equal to 0. And that is the point in which we would be dividing by 0. Therefore, that is the point in which we want to avoid. All right? So, we create these asymptotes at every time the function crosses the x-axis. Once you do that, it's quite simple. The graph just looks like this. The yellow. So first I'll graph it, and then we will explain why that's the case. So what is 1 over cosine? Secant, right? Boom. Notice that the function never, ever, ever, it has these vertical asymptotes at pi over 2 and at 3 pi over 2. The function will never touch this vertical asymptote that comes down from here to here. Okay? So let's think about this in terms of f of x table. So secant of x table. Let's just pick positive values. Let's go 0, pi over 6, pi over 4, pi over 3, pi over 2, and let's just do one more, 2 pi over 3. Notice that the secant of 0 is the same thing as 1 over cosine of 0, right? And that's 1 over 1, which becomes 1. Secant of pi over 6 is the same thing as 1 over cosine of pi over 6. Okay. And cosine of pi over 6 is what? close. That's sine of pi over 6, right? So this becomes 1 over root 3 over 2, right? So when you multiply by reciprocals, this becomes 2 over root 3. And yes, you can rationalize the denominator. So 2 over root 3 is the same thing as 2 root 3 all over 3. How did I get this? Well, this is the same thing as being multiplied by a fancy number 1. Okay. Then what is the secant of pi over 4? The same thing as 1 over cosine of pi over 4. The same thing as 1 over root 2 over 2. This is the same thing as 2 over root 2. Now, that is the same thing as, if I rationalize the denominator here, 2 root 2 all over 2, cancel, cancel, root 2. So I could have just written root 2 here as well. Just out of room. It's not a big deal. Then the secant of pi over 3, what is this equal to? That's 1 over the cosine of pi over 3. Then you get 1 over 1/2, right? And then when you multiply by reciprocals, then you get a 2. Right? Then what is the secant of pi over 2? It's the same thing as the cosine of pi over 2 divided, with a 1 in the numerator. That's going to be in the denominator. What's cosine of pi over 2 though? Oh, come on. What's cosine of pi over 2? 0. It's 1 over 0, right? We're dividing by 0. So you say this is undefined, but it's definitely undefined, but you can also kind of conceptually think about it as equaling positive infinity. That's why the cosecant function approaches higher and higher values right here as it approaches pi over 2. Who here is going to take calculus? 1? That's it? You have to take all of the calculi.
I'm taking it.
Huh?
I'm taking it.
Oh, good. You gotta love Anthony. He's still participating even though he's at home. Thank you so much. I applaud you. Yeah. Doesn't computer science make you take calculus? Oh, you don't know?
No, I don't know.
I feel like they do.
They might.
Yeah. It's really important because math and computers kind of go hand in hand.
Yeah.
Yep. So in calculus, you'll learn about a concept called limits. I won't go into it today, but truly when I say 1 over 0, it cannot equal anything. But the limit as this angle approaches pi over 2 ends up equaling positive infinity. So we can think of it as being that, and that's what visually explains this right here. These values, look, as I go more and more to the right, the y values start to go higher and higher and higher without bound. Whoop, all right, so that's why we get that asymptote right here at pi over 2. Right here. We're going to get another asymptote at 3 pi over 2. And then you realize that, okay, what is the secant of 2 pi over 3? That's the same thing as 1 over cosine of 2 pi over 3. That's equal to 1 over negative 1/2. Yeah. Which becomes negative 2. So when you pass this right here, that's why it flips. That's why it flips from opening up like this to opening down like that, because of that minus sign right here. You guys see that? Yeah. That's what's going on there. So notice that you really need cosine to build secant. Take a look. You could look at secant all on its own, and it wouldn't really make a lot of sense why that's happening. It's only when you think about it in the frame of reference with cosine here that it makes sense. Oh, it's like on the tops of the wave, and it's just doing that, and that's just because of this. The reason the secant function looks the way it does is because that's what happens when you plug it in for various x or various theta. That's what the outputs are. Very similarly, can we do this for the reciprocal of the sine function? Okay. Oh. Oh no, that's not good enough. Not for my students, that's not good enough. My students deserve the best lines possible. Okay, so remember sine assumes 0 at first, and so it goes like this. All right, you know this is 1, -1, yada, yada, yada. So then let's consider the reciprocal of sine. Cosecant x over sine of x. Recall with what we did earlier, you can get division by 0. And division by 0 occurs whenever sine of x is equal to 0. Since this white line, this white curve, is what represents the values of sine of x for an input x, we know that the asymptotes will occur right here. And right here. Just look at where it crosses the x-axis, and then you'll realize, aha, so okay, there's going to be an asymptote right here, right down the y-axis. There's going to be an asymptote right here. So what does cosecant look like? Actually, you'll realize that it just looks like this. Isn't that cool? Boom. Isn't that cool? So here's the reasons. We'll go over the reasons again. Six, power 4, power 3, power 2, power 3, for instance. Okay, what is the cosecant of 0? The cosecant of 0 is the same thing as 1 over sine of 0. Well, what is the sine of 0, guys? Oh, that's right, it's 0. Right? And then you're dividing by 0, right? That technically doesn't equal anything definable. But in mathematics, we can assign it some meaning through the idea of limits, which is beyond the scope of this course, but you can think of it as a positive infinity. And that's why, look, the cosecant function, as you get closer to the 0 for the x, the y grows without bound. If I were to zoom out here, we'd notice that it infinitesimally, oh, it's too much. It infinitesimally approaches that y-axis, but it never touches it. It looks like it touches it, doesn't it? It looks like it does. But if I were to zoom in very close, look, we notice it's not really touching it. You see that? Isn't that cool? And it actually will never touch it. Even though it starts to look like it does, as you zoom in further and further, you realize it's not touching it. And it will never touch it because you can't divide by 0. So then what is the cosecant of pi over 6? That's 1 over sine of pi over 6. That's 1 over 1/2 multiplied by reciprocals. You get that that equals a 2. Right? What's the cosecant of pi over 4? That's 1 over the sine of pi over 4. That's 1 over square root of 2 over 2. Okay? When you multiply by reciprocals, that becomes 2 over root 2. Okay? And then you can rationalize the denominator if you like. Recall if we rationalize the denominator, I'm going to get 2 root 2 all over 2, cancel out the 2's, this ends up becoming a root 2. I'll just write that out. 2 over root 2. I multiply top and bottom by a fancy number 1. This becomes 2 square root of 2 all over 2, cancel them out. If you were wondering what I'm talking about, that's what I'm talking about. Let's do it for this one. Cosecant of pi over 3. The 1 over sine pi over 3. Well, sine of pi over 3 is what? It's really early, isn't it? I'm very sleepy too, guys. So it's root 3 over 2, right? And so we flip it and we get 2 over root 3. But notice that 2 over square root of 3, if we rationalize the denominator here, that's the same thing as 2 root 3 all over 3. So,
I don't think they can see the chart.
oh, thank you for letting me know that. Other way. You know, you guys could have let me know that in the chat too. Kinsey and Anthony, let me know. I'm looking at the chat. If you guys ask anything, I'm constantly looking there to see if you guys have a question. The only reason I'm not going to have you like talk on speaker is because the sound system in here is really loud. So someone will be able to hear you in the bathroom if you're asking a question. Not that that's a bad thing. People need to, if people walking down these halls, they need to hear about math. So let's see what, okay, so then we do sine of pi over 2, or cosecant of pi over 2. That's 1 over sine of pi over 2, right? All right, but that's 1 over 1. That's 1 over 1, which is 1. And this last one, to kind of get past that hurdle, cosecant of 2 pi over 3. That's 1 over sine of 2 pi over 3. All right. But what is the sine of 2 pi over 3? Square root of 3 over 2, right? So then this is going to be 1 over square root of 3 over 2. Flip by reciprocals. This becomes 2 over root 3. And recall 2 over root 3 is the same thing as 2 root 3 over 3. So let's analyze this yellow function here. So again, this vertical asymptote is here on the y-axis because for x equals 0, that is this line. This line here is for x equals 0. And notice for when x equals 0, the function outputs, an undefined value. So that's why it's an asymptote right there. Then when we move to the right a little bit at pi over 6, it outputs a 2. So over here, here's our pi over 6 right here. If we go right here and measure where this is at, guarantee you it must be at a 2. Let's hit the home screen. Let's go to, where's pi over 6? Come on. Oh. It doesn't say it, but look, if we get really close to 2, oh, yeah. Really close to 2. Look, it says like 0. Really close to 2. Really close. Too much. It says like 0.52. Notice that that is approximately pi over 6. If you have your calculator, feel free to check. But 0.52 is approximately pi over 6. Look. See, look, 0.52. Yeah, that's why that's happening. Isn't that cool? Isn't math cool? What's really cool about math is that these weird graphs are related to the circle. And we understand the circle using the triangle. The triangle is like our microscope. In biology, the original biologists, the primordial biologists used microscopes to study microorganisms, right? To us mathematicians, the way we study the circle is utilizing the triangle. We know the Pythagorean theorem allows us to measure distances. And so we use the triangle in order to understand how does a circle change. Notice that we're going to have another vertical asymptote, and we can predict where it's going to happen at. Where, class, I'm going to put the ball in your court. Where is this vertical asymptote at? And why? Yeah. I'll give you a hint. It is located where sine is equal to 0.
It's pi, right?
Yeah, yes. I was just about to say, if Anthony was here, he would have said what many of the students are thinking. And so, yes, it's pi, right? Because cosecant of pi is the same thing as 1 over sine of pi. We know sine of pi is 0. And we can technically assign this but yeah. Okay. technically that value is going to be minus infinity. That's a way to think about it. And you can think about it as, okay, well, in calculus, the limit as I approach theta, which is pi, from the right gives me negative infinity. When I approach it from the left, it makes no sense. Actually, if I approach it from the left, it would be positive infinity. When I approach it from the right, it becomes negative infinity. None of that will be on the test. Just know it's got asymptotes. Also, graphically, it reveals it to us because you get this as the output. Okay, so that's secant and cosecant.
I have a question.
Yes, ma'am.
Can these be shifted the way that the graphs can be shifted, or they have to be independent or dependent on the graph, like the cosine? Or
That's a great question. Why don't we just find out here? All right. Let's assume I have no idea. How can we test that? Let's try and induce a shift, right? Let's try and induce some type of horizontal shift here. What do you want to horizontally shift your cosecant by? Let's do something in terms of pi.
pi over 2?
Okay. Boom. Let's see what happens here. Here was our original cosecant. What happened when we do a horizontal shift by pi over 2? Take a look. The pi over 2 now moves over to pi because the horizontal shift shifts everything by pi over 2. And so pi over 2 plus pi over 2 equals pi. Does that make sense? So yes, absolutely. So what would happen if now I put a negative on it? That one's a little harder to see. What would happen if I were to change its amplitude? That one's easier to see. What would happen if I were to give it a vertical shift? You see that?
So it's not dependent on the, in this case, the sine graph to shift, right? Or
All the rules apply. So when we said that there was rules for it's so hard to erase. So yeah, we said you know, for instance, y of x in general is equal to a. I said sine, but it could say cosine. It could say cosecant. We're talking about secant here. We're talking about cosecant. Everything still applies. A is still the amplitude. B still allows you to determine the period. 2 pi over b is equal to the period. Your ratio of c over b still tells you what kind of horizontal shift you have, whether to the right or to the left, based off of your c over b being negative or positive, right? And then your vertical shift d still does what it would do before.
but so when we shift the cosecant graph, it gives us a new sine graph, right?
Ah.
That's what I'm trying to ask.
Oh, so yeah. Now, okay, so this is gonna look really beautiful. Look at this. Here's cosecant, right? Let me put just sine of x minus pi over 2 plus 2. Ta-da! Isn't that cool? Yeah, man. Yeah. Yeah, because cosecant is built off of sine. Cosecant is 1 over sine. So if you have the same sine and you cosecant it, you could just, this is what I'm saying, just draw the function in terms of the sine or the cosine, find out where the vertical asymptotes will be, and then you'll be able to create the cosecant graph each time. So this is something you guys need to, I highly encourage you to use this website, Desmos, desmos.com/calculator. It's a really beautiful website. It graphs things really nicely. And every time you create a new graph, it puts it in a different color. So visually, you can see it very well. But yes, that's not a coincidence that this happened here. This is not a coincidence. The same would be true if I then said cosine. And what is the reciprocal of cosine? Ooh.
So anytime that we shift by secant or cosecant, we have a new cosine or sine graph.
Yes, yes, ma'am. Yeah. And I actually suggest do the cosine or the sine first, and then it's easy to see how the secant or the cosecant will be. It's just like this. Notice where you're dividing by 0 is when the function would be crossing the x-axis. Now that there's the horizontal shift, you can't see that visually, but when you create a table, when you tabulate it, you'll realize where it's occurring when you're dividing by 0. Any questions? Very good. I'm so proud of you guys. You guys are asking great questions. All right. So now it begs the question, now that we know this stuff, it's kind of begging the question here. Let's go back to sine. And let's go back to cosecant x. This is begging the question, well, if I know what the period of sine is, it's what? 2 pi. What is the period of cosecant? Is it 2 pi?
No, because it doesn't reach all the way to 2 pi.
It doesn't reach all the way to 2 pi.
It goes up.
Let's click on some values here. You guys are coming up with really good conjectures. In math, a conjecture is a unverified guess. Okay, so here's all our points of interest. Okay, the period is defined as the length in x you have to traverse for the function to repeat itself. So this is why this function is going whoop, up, down, whoop, and then back up. Whoop. So for it to repeat itself, it had to be a 2 pi distance. How long for cosecant to repeat itself? So let's see, like right here, boom. For instance here, at pi over 2, how much x do we have to move for it to reproduce itself here at 5 pi over 2? Well, one way to think about it is to say 5 pi over 2 minus pi over 2. This is 4 pi over 2, which is equal to 2 pi. And this gives weight to Travis's conjecture that it's 2 pi, right? But we gotta have to kind of think about the cosecant function. And think about it in a way in which is slightly different, because it's kind of hard to see it visually here. Okay, but the actual period is technically pi. And here's why. the cosecant function is not like the sine function where it goes up and then down and then back up. All it does is just sweeps like that. So its repeated value over here is its repeated value over here. It's more scrunched than the sine. So notice that the distance from here to here is pi. So this is just a overly technical example, but it's technically pi. And all integer multiples of pi. So the period of, which one is this cosecant? Cosecant x is equal to all the values in which your x does not equal a n pi. So all integer multiples of pi. And notice 2 pi actually works when n is equal to 2, because we can't have x equal to 2 pi. So technically 2 pi was right as well. It's just it doesn't encompass the pi. So we have to alter it to this. So I could set n equal to 2 and I would get a 2 pi. So 2 pi was still correct. It just didn't encompass all of them. All right. So what is the range? So what am I saying here? This is the domain of cosecant. Domain of cosecant. It's all the inputs that can't equal 2 n pi. Period is just actually just n pi. Okay. So let's talk about the range now. What does that equal to? The range is all of the possible outputs of the function, the green stuff. So we notice that the green stuff, here it's like at 1 and it goes all the way to positive infinity. And over here it's at -1 and it goes all the way to negative infinity. So in interval notation, we say that, okay, it can range from all the way down to negative infinity, all the way to -1, and it includes that point. So I put brackets.
I don't think they can see it.
Oh, thank you. Thank you, Pamela. Is Pamela or Pam?
Either one.
Prefer Pam?
Yeah.
Prefer Pam, okay. And then union 1 positive infinity. You guys see that? You guys see why? Yeah, it's just visual. You just look at it and you see that that's what's going on. That's why I really like math. I like visual stuff. I like pictures. You know, who doesn't like pictures? Who likes opening up a book and there's nothing but words? You know, pictures are cool, right? So math kind of, the more you can make pictures out of math, the more you can understand it, in my opinion. That's what mathematicians really do when they try and understand something that's really convoluted. Then what they do is they'll draw a picture to try and visualize the situation. Now, let's shift, no pun intended, our focus onto the other reciprocal. Oh, man. Oh, this is torture. To even scrub the board. Okay. See here. So I don't write it off. There we go. So then we did cosecant. Let's do secant. What is the domain of secant? You know what? Let's just look at it. I know I can build secant off of its cosine graph. Bam. So then, let's take a look at it. What is the domain? The domain represents all of the inputs that don't mess something up. And we notice that the only time this messes up is at these vertical asymptotes here, vertical asymptote here, vertical asymptote here. So we know that the domain is a set of all x, set of all inputs x, such that they don't equal what? One of the vertical asymptotes is at pi over 2. One of the vertical asymptotes is at 3 pi over 2. You know, it's all the points in which cosine gives you a 0. Pi over 2 and 3 pi over 2, right? Pi over 2, 3 pi over 2. Let's think about pi over 2. And then let's think about 3 pi over 2. Notice that if I get a pi over 2 and I add a pi to it, what do I get? Yes. Yes. So this one is almost redundant, is it not?
2 pi or pi over 2.
It's just, it can equal a pi over 2, right? Let's just put it over here. But we got to also say, you know, something. Integer multiples of that. Oh, wait, no. Not integer multiples of that. It's pi over 2 plus integer multiples of pi. Because here we added a pi and we got that other value that it couldn't be. Really, this is the way you can think about it. Get the unit circle. We know that cosine is 0 here and cosine is 0 here, right? This is pi over 2. This is 3 pi over 2. Notice that n pi comes from any time I add a pi or subtract a pi or add a 2 pi or subtract a 3 pi, any integer of pi just sends you to somewhere which should be dividing by 0. So that's why that's the case. I'm trying to like show you why this is true. Technically for your tests and quizzes and exams, it can be like an assumed fact, but I don't like you guys to memorize. I want you guys to understand. That is a much higher level. It's a much higher level of reasoning, intellectual potential. So let's say you're coding. You can't just memorize code. Coding is like an art form. You have to know what you're doing, you know? You can memorize that, okay, this command causes this output and this other command causes this another output. But you can't memorize code, right? Because every time you create a code, it's specific to this very situation. What kind of programming languages are you familiar with?
Java, JavaScript, Python.
Python, yeah, okay. Yep. So They all have their own languages, right? Yeah. And you have to memorize that, okay, if I want to print, I have to say something, something, dot this, squiggly line, slash this, and then input it, and then it will know, okay, you want it to print a string or something, or a number. But after that, you have to kind of understand what's going on. So like for loops and if loops, if else, stuff like that. So I hope that math helps you guys improve your critical thinking and reasoning skills. That way you can apply them to anything, being a MD, being a math teacher, being a computer programmer. I don't know yet for Travis. He doesn't know yet either, but you'll figure it out. I want you to become a mathematician. I'm lobbying all of you to be mathematicians or theoretical physicists. But you know what? You don't have to do what I think is awesome. I think coding is awesome too. And I think teaching is awesome. And I actually almost became an MD. I think that is awesome too. Physiology, man, infectious disease, that stuff is really cool. There's this show I really like watching. It's called Monsters Inside Me. Have you heard about it? You have? Have you seen that show?
I haven't seen it, but I've heard.
Oh, you need to watch it, man. Every person who wants to be a doctor should watch that show. It shows like case studies of different parasites and how people get them and what they cause. Right now, there's a brain-eating amoeba in the water in Texas. Have you guys heard about that? Yeah. One of them is, you have heard about that? Yeah.
A little boy that died because of it.
Yeah. Yeah, one of the brain-eating amoebas is called Balamuthia mandrillaris. Another one is called Naegleria fowleri. There are different kinds of amoebas that, you know, if you just drink it, nothing will happen. Your stomach acid will dissolve the amoeba and kill it. But if it goes up your nostril at the right trajectory, at the wrong time in your life, it can affect your brain, and there's almost, I believe, like a 95% chance you won't make it, because we don't have any antibiotics for that amoeba that work. So it's a very rare infection. It's a very rare kind of infection, but it's still really cool. maybe one day, one of us in here will discover a treatment for it. Okay? So now that we've discovered the domain of secant, what is the range of secant? Interestingly enough, there's computer programmers that are able to test theoretically whether certain like drug mixtures will work, if you will, for treating a disease. There's software and code that is now like starting to predict that. Therefore, you have like less mice that have to die and stuff like that. You can kind of test whether this will work or not. And that's really cool. So everything we do in here is really cool for helping humanity. Okay. What is the range of secant? This is our secant. Notice visually, it goes from -1 to negative infinity and +1 to positive infinity. So it has the same range as the cosecant. Okay. We did sine and we did cosine. We did secant and we did cosecant. That's all the trig functions, right? Oh, how could we forget tangent? Guess we're gonna have to do that one too, aren't we? That one's important. Tangent of x. What does cotangent? Wait, does everybody understand why tangent of x even looks like this? First, have to talk about why tangent of x looks like that before I can show you cotangent of x, right? I'll just show it to you real quick. Yeah, we'll see why that happens. It's really cool. We'll see why that happens right there. first address tangent. Why does tangent look like that? It's just a consequence of the f of x table. Jeez. So let's create our table. Here's tangent of x. Let's pick some values. Let's say 0, pi over 6, pi over 4, pi over 3, pi over 2. Let's say 2 pi over 3. What is the tangent of 0? Well, that's the sine of 0 over the cosine of 0. Right? But the sine of 0 is 0. Cosine of 0 is 1. Right? And when 0 is in the numerator, the whole fraction is 0. So we put a dot here. What is the tangent of pi over 6? That's the same thing as the sine of pi over 6. Or the cosine of pi over 6. Okay? That's a half over root 3 over 2. Right? But when you multiply by reciprocals, this is what you get. And notice we can cancel out these guys here, and I get 1 over root 3. And when you rationalize, that's the same thing as root 3 all over 3. What is the tangent of pi over 4? That's the same thing as sine of pi over 4 over the cosine pi over 4 is root 2 over 2 over root 2 over 2, which is 1. So over here, we'll come over here, pi over 6. And we notice it's like at root 3 over 3. What is root 3 over 3? Oh, it's around 0.75. I mean, dyslexia strikes again. 0.57. So that's around like right here. Okay. If this is 1. And then, what about pi over 3? At pi over 3, it's a tangent of pi over 3, which is sine of pi over 3 over cosine of pi over 3. Right? Which then I get root 3 over 2 divided by half. Right? So when you multiply by reciprocals, you get that. So notice then 2's cancel and I get root 3 over here. What is root 3? I believe it's like 0.7. Oh, 1.7. Square root of 3 is like 1.7. Okay. So pi over 4 tangent is right here. And then pi over 3, it passes it right here to like 1.7. So notice it's just continuing to rise and rise and rise and rise. But what happens? It seems like it doesn't continue to keep moving to the right forever. It seems like there's a vertical asymptote, if you will, here at pi over 2. Is it not? Well, that's because we're dividing by 0 at pi over 2. Sine of pi over 2 over cosine of pi over 2. Cosine is in the denominator. When cosine is pi over 2, it evaluates to 0. So this is the same thing as 0, or 1 over 0. So this is why our tangent graph is just rising and rising and rising when we get close to pi over 2. And then it breaks. There's a vertical asymptote here, and then it starts all over. For the negative values, you can see that if you do this tabulation, it would get this. With the vertical asymptote over here at negative pi over 2. And it just repeats. You can see if you graph it for yourself that it just repeats. This phenomenon repeats. Where this would be at, what value do you predict this to be at?
Three pi over 2.
Oh, not a bad prediction. Why do you say that, Anthony?
Well, because the value will be undefined because negative 1 over 0, which is, the sine is negative 1 over 0, which is cosine, is going to be undefined, so that's where it needs to be.
Yes. That's why you get the vertical asymptote, because you'll be dividing by 0. Okay? So, now we know what tangent looks like and why tangent looks the way it does. What is the period? Yes. Because the distance between the asymptotes is pi, and that's when the values repeat. So yes, the period is pi. Okay. What is the range? What's the range? Oh, we said that the domain. I don't talk about domain. I'm asking you about range. What does that red graph range from?
Infinity.
Yes. Positive infinity. All values. It ranges for all values. What is the domain? The domain is all the inputs that don't cause tangent to mess up. The vertical asymptotes are the points in which tangent messes up. So
it can't be n pi?
Yeah, you're right. It can't be n pi. It's the set of all x's where x cannot be n pi. Over 2.
Wait, why isn't it just n pi and what, or why is it n pi over 2?
So there's two ways of saying it. You can say it can't be pi over 2 plus an n pi. That's another way of saying it. Another way of saying it is it can't equal n pi over 2. They're both equivalent, but that's also equivalent to that. Now, without further ado, why does cotangent look like this? Notice, huh? Oh, okay, I thought someone from the internet was gonna say something. Oh, is that you?
Oh, no.
Oh, is that you? Okay. Notice they agree at pi over 4. What is cotangent defined as? 1 over tangent. So one over tangent. If tangent is sine over cosine, then 1 over sine over cosine is it not? Okay. So this thing is going to have undefined values when sine is equal to 0, right? When is sine equal to 0? At 0, at pi, at 2 pi, at 3 pi. So notice here at 0, this purple, which is the cotangent, has a vertical asymptote. And right here, over here, it's going to have a vertical asymptote at pi. Well, okay. Right here. This is pi right here. Notice that, boom, there's a vertical asymptote for the purple right here at pi. Because the cotangent of pi is cosine of pi over sine of pi. That becomes like a -1 over 0. You can kind of think of it as negative infinity. That's why it's headed down at that point. That's why the purple is headed downwards at that point. Okay. So what is the domain and what is the range of cotangent? Oh, what's the period as well? It's actually going to be very similar. Okay. Domain is a set of all values it can accept. So what is the value that it can't accept? It can't accept 0 as an input. It can't accept pi as an input. It can't accept 2 pi as an input. So x cannot equal n pi. Right? What is the period? It's the amount of horizontal translation it takes for it to repeat. And you'll notice that the distance from this vertical asymptote here to this vertical asymptote here is pi. So the period is pi. The range is from okay. Let's see if there's anything else here. Oh, I know what you're thinking. Does the shift stuff work for tangent? Let's do a horizontal shift. Boom. Let's do a vertical shift. Let's change its amplitude. Whoa. 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 So yes.
If we change the amplitude enough, would we be able to make like a straight line, or would it always be a curve?
Good question. What if the amplitude is like, it's almost like a straight vertical line, isn't it?
But I'm guessing if we zoom in, it's still gonna be.
It's gotta have some curve to it. Feel free to play around on Desmos. It's really fun. Okay. So that's it for today, guys. I'm gonna let you guys out with 3 minutes remaining. You guys have been really good. Let me know if you guys have any questions. Let me know if you need any homework extensions. If something happens in your life that you're not able to like get the homework done on time, send me an email. Let me know. I'm willing to work with you. Don't get too used to doing that. But yeah, if for some reason you can't complete an assignment and you want more time on it, let me know. I'm reasonable like that. Okay? I just want to see all of you guys do well and succeed. You're welcome. Have a good day.
Hey,
See
Professor.
you later. Thank you, Anthony. See you, Harrison. Yes, sir.
Can I just email you my homework?
Sure. Yeah, send pictures. Send pictures
Sure.
of it. Yeah,
Got
that
it.
works.
Thanks so much, man.
You're welcome. You're welcome.